Welcome to Alaska Earthquake Science Facts. I'm Carl Tate. The tectonic plate has been subducting under southern Alaska for at least the past 200 million years, as evidence from the geological record in the Cook Inlet region. Here's a photo from Cook Inlet of an oil platform with the volcano spur in the background. And these are very large. So these are multi-story, person is just tiny figure on these multi-deck platform. The question is, for Spur Volcano, why is it here? And for this oil and gas platform, why is it here? And we'll see that these answers are connected. At a large scale, they're both due to subduction. They're very different manifestations of subduction. Spur is part of the Aleutian Alaska arc of volcanoes. It erupts and forms over human history, most recently in 1992. Oil and gas comes from organic rich material deposited in the ocean 170 million years ago, the Tectonic group, deep below Cook Inlet. The subducting plate influences the creation of this volcano and also this physiographic depression that holds the oil-rich sedimentary layers. Here's our view as a reminder for subduction in Alaska. We have the Pacific plate moving. In this case, it's an oblique view. It's moving north-northwest. And under the trench, it dives below North America, as shown here at the boundary. And this is the arc of volcanoes. And we'll be focusing on the Cook Inlet region, for example, where Redoubt Volcano is. Here's an extraordinary map of Cook Inlet Sedimentary Basin. It's not easy to see what we're looking at or the scale. The Cook Inlet, the body of water, is shown overlapping this area here. This is the Kenai Peninsula. Anchorage is right here. Kenai, Soldotna, and Nikiski are in this region of the western Kenai Peninsula. These green and red dots are showing oil and gas fields in the Cook Inlet region. And the reason we have such a detailed map is due to exploration by oil companies and governmental bodies to better understand the geological formations in this resource-rich area. So the map by Diane Schellenbaum and others at the Division of Oil and Gas in Alaska, top Mesozoic unconformity depth map of the Cook Inlet Basin. If you're an introductory student, there's a lot of words there. I would translate that as a bowl of sedimentary rocks that are 66 million years and younger. And these contours are showing the depth of this boundary. And so red would be near the surface, and the blues down here in the center would be the deepest parts of the basin right here near Nikiski. And we'll zoom in so that we can see some of the details in this map. Here's just a cutout from the middle of the map. Again, it's not easy to see the coastline, but here's the coastline of Cook Inlet here for reference. And on the other side, you can see coastline shown right here. And I'll overlay some Google Earth images, but what you can see here, these are contours in thousands of feet. So imagine 20,000 feet below sea level is the boundary of this basin containing sedimentary layers. And this is the very center at 25,000 feet below sea level. So here's an overlay with Google Earth. You can kind of get a better sense of where this basin is. It's onshore, it's offshore. And so here is Nikiski, Kenai, the Swanson River oil field. And this is the depot center, the deepest part of the basin. So you can get a sense of where this is. So I'll go back one more time just to see. There's the sedimentary basin map, and this is all showing us information deep down. So these contours are going down. We're used to often seeing contours going up. These go down. Okay, so the maximum thickness of the Cenozoic sedimentary layers, these last 66 million years, is 25,000 feet or 7,620 meters. It's really a staggering volume of material of sedimentary layers being deposited here, and we'll see what makes this globally exceptional. Just looking at a cross section of that, both the topography and the basin, not even in the deepest part of the basin, but something through Redoubt Volcano, it's highly exaggerated topography. So this is distance in 100 kilometers, 200 kilometers. Um, but what you can see is that Cook Inlet Basin is far deeper than these spectacular mountains on either side. So when we look up at the Kenai Mountains or Redoubt Volcano, it'd be good to think as well, think about what's down below, a much larger volume of material being stored and preserving a record of an ancient history of subduction here. And what is this ancient history? Well, it's preserved in the geology below. In the basin, these are synthesis of all the different material as you go from top, the youngest material, to the bottom. So these are stratigraphic sections, Fisher Magoo 1978, and a compilation from the Schellenbaum map. And so based on seismic imaging, well logs in the basin going down, and a lot of careful mapping of outcrops around Cook Inlet Basin, geologists can piece together the maximum thickness of each of these sedimentary units, Sterling, Beluga, Tectonic, Hemlock, and the maximum thickness gives us an idea of if we could go 7 kilometers down or even deeper, what we might expect to see in terms of thickness. So this upper unit are the younger sediments on top near the surface, down to this boundary right here, the top Mesozoic unconformity where we were seeing in the map, that represents in this map 6,960 meters from 1978. As we saw the recent compilation in 2010, that's something like 7,600 meters. Below that map, though, there's a much thicker and older history of sedimentation and subduction here. So below that, and this on the left here, the Mesozoic units from 66 to even 252 million years, at least that time period is represented. There's actually a max thickness of 12 kilometers below the map I just showed. So taken together, the max thickness would be something like 19 kilometers of sedimentary layers in Cook Inlet. And this is shown the older units here, and you can see this Tuxedni. That's the unit where the material that sources um, the oil and gas in Cook Inlet is mostly from this formation. So this is an interesting way of looking at time and depth in a place that has a very long record of sedimentation. And we'll see how geologists take this information to understand the plate tectonic history in the area. So two overviews just to point out, this is two papers if you want to deep dive into Cook Inlet Basin and looking at how basins are a fundamental part of the history of Alaska. This is a paper by Dave Lapine and others, something like 80 pages, a really large overview, 2014 paper. And this is by Trop and Ridgway, looking at a basin focus a little broader than Cook Inlet. This is a figure shown in the introductory video, sort of generic subduction profile, where we were starting to label where are the features in this generic setting in Alaska. And one of the pieces was this Cook Inlet four-arc basin, the idea that in many subduction settings, you have a basin that is in front of the volcanic arc. So that's what the four refers to. It's in front of the arc. And here we see, we could think of this as Redoubt Volcano, magnitude 9 earthquakes along this interface, but one plate's going below the North America plate, and we're interested in looking at this Cook Inlet four-arc basin. This is a complicated image that shows a lot of information about the magnetic and gravity measurements across Cook Inlet Basin. So this is looking from southeast to northwest. This would be the Pacific plate going down under the North America plate. And these images are tying together the author's interpretation and modeling of the subsurface structure in terms of the magnetic properties, shown the high magnetic body here, and also the density. So here, these very low densities, this kind of bowl shape right here. This is Cook Inlet Basin. You can see this would be, about 15 kilometers here of material, giving a very low density signature as shown with this depression right here. But in fact, in the subduction zones below that are higher density material of a slab coming down, even this body right here, higher density. And that's the pull that as the slab goes down, it actually pulls and creates space for all these sediments to be preserved. So this is common to many subduction settings where you have fork basins, but there's some large scale pull from subduction of this plate going down that creates space for all the sediments. So what makes Cook Inlet Forearc Basin and the subduction setting globally exceptional? I'll put two ideas forward. One is that subduction is really old here. It's been going on for a long time, and also the basin is thick. How can we back that up? Here's a compilation by Gerard in 1986 looking at all the subduction zones and basic information he could find about all these different subduction zones. So here we are in Alaska, and that's one of the places he examined. You don't need to read all this, but it's to convey that this is a really large scale compilation of information about the dip of the slab, the extent of the slab, convergence direction. So each row is a different section of a subduction zone. And this is just half the table. So here's the second half, convergence rate, time sense subduction, age of the plate, all these things in here. And what we're interested to see is that the label for the age of the volcanic arc in Alaska. So something about how long subduction's been going on that might give us some idea of the setting that we have today in terms of earthquakes or convergence. And what we see in Alaska is 160 million years of subduction. That was in 1986. Since then, this age has gotten a little older, and these are two examples, Sarah Ruski and others in 1989, and a paper in 2010 identifying from rocks, in particular on Kodiak Island on the northwest, Afognak Pluton, that the age of the arc is probably more like 210 million years old. It's a very long time for subduction to persist in the same place. Moving on to the characterization of subduction zones, Clift and Vanucci have a global compilation, and they basically said that there are two types of subduction zones. Ones that are erosive, where there's not much sediment coming down on the plate, and this plate comes in and basically scrapes off material, eroding the upper plate. And there's, as they shown here, kind of profile, but the wedge is one of the big differences between these two. The other kind is an accretionary subduction zone where lots of sediment is coming in and there's this large accretionary wedge and lots of thrust faulting shown here, underplated sediment. So this is the category that Alaska falls into. And we can think of this as Cook Inlet and Redoubt, again, to try to tie our setting into these generic profiles. This shows the accretionary subduction zones of the world, and they've labeled these different forearc basin deposits as the one that we're interested in. And you can see here's Vancouver, the Aleutians, Sumatra, all these different deposits. We can see the depth scale on the vertical axis, and hopefully you'll see that the one for Alaska is actually the thickest. It's about over 10 kilometers. So this is shown that image right here of about 10 kilometers. And you can see the endnotes here to get some more details on this particular profile, but it's an exceptionally thick forearc basin. So Alaska is a puzzling place of terrain pieces, and this is captured by this puzzle made by Roger Topp for a museum exhibit where we're trying to convey that Alaska is made up of a lot of pieces that have come from far away at different times. And you might want to think of these pieces as how did they get here? When did they get here? But there's also this sort of on this side, this is like the old North America, older rocks, stable, and Alaska is pieced by these chunks and puzzle pieces coming in at different times. And so our emphasis here is on Cook Inlet, which is right here. So I'm going to show a set of very complicated pictures of how geologists pull together everything they know about Alaska and get to a complex setting, which is of today. This shows the outline of Alaska, and all these red things are active faults. The teeth represent thrust faulting of this Pacific plate here going down under the upper plate. So this represents thrust faulting, whereas this label represents strike slip faulting. So here's our present day tectonic setting. The question is, how did we get to this state? What a large mystery that will always remain to be discussed and tried to understand. But here's one take from 1994, and we're going to keep our eyes on. They've given us Anchorage just for reference. Obviously, Anchorage wasn't around in these times, but it gives us a point on the Earth to watch where it tracks. And here is Cook Inlet Basin, this small area right here, which is the focus of our discussion. So geologically speaking, Alaska has not been around forever. So even though you see this outline of Alaska on this map, they're just giving that for reference of where we go in the end of this sequence. This is 570, 360 million years ago. And it says this is sort of stable North America, present eastern edge of the Cordilleran origin. And this shows all of during this age, different kinds of rocks that we now know where they are, but the authors are trying to infer how they came during this time period to connect with North America. So this is a long time ago, and we'll move forward in time. So here's 360 to 230 million years ago. We see this A for Anchorage as some subduction arc far away, unknown exactly where this is, but it's basically on a ride up to collide with North America. 230 to 160 million years ago, I'm going to show at the right the Cook Inlet stratigraphic column. So this is just the layers in one particular part of Alaska, but the one that we're interested right now. And so I'm highlighting in red the time period of deposited sediments that are inferred to be below Cook Inlet Basin and that appear in some outcrops on the margins of Cook Inlet. And we can see during this time period, these are the materials being shown. On the left there we see Anchorage, and it labels Talkeetna Bonanza Arc. So this arc is showing the kinds of material that's being formed, and then sediments eroding away from these arcs, deposited in marine settings. So this is showing the earliest stage of the start of Cook Inlet Basin. So it's the deepest part here, and this is a picture of where in space this may have been. Again, Alaska hasn't even really been formed tectonically at this point. It's in the process of. 160 to 120 million years ago, we've moved up in the stratigraphic section to younger material. More things have been formed here in Alaska. You can see this arc setting. There's Anchorage shown, this thrust fault, subduction continuing, sedimentation. Still moving up 120 to 84 million years ago. Here's Anchorage, here's this arc, all these sediments shown here and forming. 84 to 66 million years ago, getting closer, you can see the Denali Fault system has formed, a lot of other activity in northern parts of Alaska. 66 to 50 million years ago, it's starting to resemble the tectonic setting in Alaska a little more. Here's Anchorage again. Still have this subduction going on out here as indicated by these teeth section. And in the last 50 million years ago, the shallowest parts preserved in this bowl of sediments in Cook Inlet. We see Cook Inlet Basin labeled right here and Anchorage here. So this shows as we go up in this geologic section, a lot of this type of information can be used to help inform the details of how a particular region came together by understanding in great detail the kinds of information preserved within these formations. So that's a view of tectonic assembly of Alaska. I'll show an alternative or a different perspective, even more zoomed in. This is from a paper by Ridgway and others. You're kind of looking to the north. This is west, east, and this is looking, you can see subduction going forward. So it's like you're on the Pacific plate or the subducting plate and looking at during this time period where here's a volcanic arc and there's submarine slope deposition and elongate forearc basin. So sediments are coming in during this time, and these would be the age of the sediments that are preserved in a place like Cook Inlet. From 60 to 35 million years ago, we'd be going up in the stratigraphic section. This is giving us Anchorage for scale. And now it says CI, that's Cook Inlet, and it says fluvial lacustrine deposition. So basically rivers and lakes forming the kind of deposition. And here the slab is going down, as I mentioned earlier, kind of pulling down and creating accommodation or space for all the sediment to be preserved. And in the last 35 million years ago, this is again Cook Inlet, Anchorage, and continued deposition here of the Pacific Plate going down under North America. And this ties into some other topics where moving more toward the east, there's this shallow subduction of an oceanic plateau, and this comes up in several of our Alaska science facts. Our emphasis is here on the more normal subduction section here, but the authors are saying that this microplate or Yakutat oceanic plateau would influence some of the activity to the west. So that was a complicated assembly of tectonic history, but the takeaway might be for that section that Alaska is made up of a lot of pieces. These pieces have come from a long ways away. They've formed at different times. And it's so this theme is a good one to think about. And keep in mind that there's this stable, older chunk of North America, and Alaska really isn't part of that story. It's got a more dynamic and frankly exciting story. So I haven't said anything about seismology or earthquakes here. So you might be wondering where the earthquake part comes in, and I'll just allude to that in these last slides. First, there are active faults out in Cook Inlet. So we saw that there's oil and gas. There's this bowl of sedimentary layers, but there are active faults. This is from the Alaska DGGS active fault map. This is Anchorage, Elmendorf-Richardson Base. This is Kenai Peninsula. So these purple lines and yellow lines, and up here, strikes at fault, denote active fault. So earthquakes occur in here. And on the right, this is from a paper showing that there are crustal events, small earthquakes that appear to be thrust style faulting in this area. That's not surprising given the compression in a subduction setting. There's also a 1933 large earthquake, something like between magnitude 6 and 7, that occurred out in this region and produced very strong shaking. And that's inferred to also be in this region. So not only are there earthquakes faulting, but they can be pretty large earthquakes and potentially a hazard for people and infrastructure in this region. The structure itself poses a seismic hazard by amplifying ground motion. And this shows two snapshots of a computer simulation of a magnitude 7.1 earthquake that occurred in 2016, right here in this blue dot, but it's pretty deep, 120 kilometers deep. And what you can see is that this is the basin. It's the basin trapping the seismic wave field as this shear wave front approaches Anchorage. This whole area captures all this wave energy and it reverberates around. So even after the wave is gone, you see this strong reverberations of energy in the basin. And this isn't just a computer simulation that we're guessing at. We're trying to take the detail of the Schellenbaum basin and structure and try to use it to get an idea of how the ground motion is influenced by that. And so this shows you the signature of that basin. And some consequence during that earthquake, here's in Nikiski, which is right near the depot center, the deepest part of the basin, where strong ground motion is expected. And this shows where a gas line was ruptured, fires occurred, some homes were destroyed. And if you look at the reports of people of where the shaking was strongest, even though the epicenter is here, shaking was strong on the western Kenai Peninsula and stronger here even than places that were, say, closer to the earthquake, such as the eastern Kenai Peninsula right here. So this is a map showing the shaking intensity. This shows the consequence of that strong shaking, even though this earthquake was quite deep and not exactly right under the Kenai Peninsula. Takeaway topics. Subduction in the Cook Inlet region of South Central Alaska has been occurring for the past 210 million years. It's one of the longest lived subduction settings in the world. Cook Inlet is underlain by a deep basin containing several kilometers of sedimentary layers. This active forearc, that is in front of the volcanic arc, basin is one of the deepest in the world. The first oil discovery in Alaska was in Cook Inlet Basin, 1957, in Swanson River on the Kenai Peninsula. The geometry and subsurface structure of Cook Inlet Basin is determined from two things: extensive geological mapping of outcrops at the surface, and also seismic imaging of the subsurface from active sources, and also data collected from exploratory wells. Thank you for watching. Please stick around for supplemental material. Just a note about the subduction profile in Clifton Benucci. It's from a paper by Von Huene in 1998. And the profile is a little bit to the south through Stevenson Basin, but I think even if it went through Cook Inlet, you'd still have a max depth of at least 7 kilometers and perhaps as much as 20 if you consider the Mesozoic sedimentary strata. And this shows the profile that they used was through, this is Kenai Peninsula, so it's to the south through this profile where we have this Stevenson Basin that was used with this, get this 10-kilometer depth. And lastly, I'll just show, this is a video on YouTube where the simulation has come from, but you can, I'll play it here, get an idea of the timing. There's the P wave, there comes the S wave, and you'll see this wrapping around and trapping and amplification as the wave field passes through. So you can check out these kinds of simulations from the playlist or from other places on the internet.